Hello and welcome to a new video. My name is Herwig Juster and welcome to my presentation entitled Designing a Sustainable Future with Polymers, a Life Cycle Perspective. So let us jump straight into the agenda I prepared. So we start with a short introduction followed by understanding life cycle engineering, LCE, then why focus on polymers for sustainability and scientific concepts and methods used in life cycle engineering for polymers. Then I will show you some approaches for sustainable polymer management and closing with conclusion and an outlook. Okay, let us get started with first, number one, introduction. So who I am. Just briefly, Herwig Juster, my name originally from Austria, over 10 years active in plastics industry at global plastics manufacturer in different roles, application development, business development, key account management, focused on high-performance polymers, material selection, plastic part design combined with plastics also for recycling and also metal replacement. My educational background, I studied polymer engineering and science, and I did a PhD in the field of polymer injection molding. And what are my motivations? So I'm a believer that plastics are part of the solution, not the problem. It's the reason I founded also my blog, findoutaboutplastics.com, in the year of 2014. And I authored also a book called Polymer Material Selection. And when we look now into nature is built on 5 polymers. We have cellulose, chitin, lignin, proteins, and nucleic acid. However, our modern life is built on over 200 different polymers. So polymers and plastics are an essential part of our daily life. However, we see a growing concern about their environmental impact, for example, plastic waste, global plastic waste management. Therefore, there's also a focus to shift towards environmental impacts of plastic products across all the stages of the life cycle. So from raw material extraction, manufacturing parts, transport the parts to the customers, the use phase, and also then disposal and recycling. And when we look at the role of materials, so the material choice for the product is crucial for achieving also sustainability. And when we look on the left lower corner, we see the 4 most used or the share of materials, and with 84% ceramics in the lead, mainly concrete, followed by natural, so wood and metals, steel, aluminium, and polymers are just 1% by volume, 0.4% by weight, dominated by commodity plastics such as polyolefins, polyethylene, polypropylene, PVC, and PET. And the global plastics consumption currently is around 370, more towards 400 million tons per year. However, this is still small compared to 90 billion in metric tons all over material use. So using more polymers for achieving certain goals is absolutely no problem. And we see it also in the growth. We always hear the argument plastics are growing exponentially. It's also not true. They have the same growth rate as other materials such as bricks or concrete. Let's discuss life cycle engineering. What is this? It's a holistic approach which allows to evaluate environmental impact, social impact, and economic impact throughout the entire life cycle. And we focus today on the application of life cycle engineering principles and also methods towards polymeric materials for sustainability. This brings us to number 2, understanding life cycle engineering, LCE. So what is life cycle engineering? It's a comprehensive methodology. It allows us to develop specification for products, systems, processes, or facilities, and in order that we meet a predefined set of performance, cost, or environmental requirements. And there are core concepts of life cycle engineering are called either cradle to grave. So, and you see that on the right side in orange. So going from the beginning till disposal of the product. The ideal state is cradle to cradle, so to keep the materials in a circular economy. However, there are also other approaches like cradle to gate. So it depends really on your specific aim. A crucial part of life cycle engineering is the life cycle assessment, the so-called LCA, because that allows us to quantify the environmental burdens and also the potential impact of our product. And when we look now at the key stages in a product's life cycle of polymer, so there we have the raw material extraction, so we need to obtain our feedstock. Then we generate our monomer, and then we come already to manufacturing. So we make polymerization, we generate a polymer, then we shape it with injection mold or extrusion or other processing technique and create a product, assemble it, then distribute it to customers, to us via transportation. And then there's the use phase where the product is used, and then comes the end of life, UL, disposal, recycling, or other management option. And important is the holistic view of all these stages. And we need also to avoid to shift the environmental burden then from one stage to another stage. Okay, now number 3, why focus on polymers for sustainability? I already mentioned in the beginning, nature is built on 5 polymers. Our modern life is built on over 200 different polymers, and polymers are really versatile. So we can achieve a lot of things. We can have lightweight product, we have durability, we have flexibility, and also cost effectiveness. But not only that, when I look at the key characteristics of polymers themselves, we have strength and low density. We have a design freedom, so we can design complex parts and mold them into our desired geometries. We have ease of processing due to the lower temperatures compared to steel or metals. We can design the durability into the material and then also into the part. We have biological and chemical inertness. We have electrical and thermal insulation. We have high specific modulus of elasticities, and this allows us also for metal replacement. Then we are also cost effective, and we have low production costs when we look in particular to commodity plastics. And this allows us also to keep up with the global demand and generate lots of great products. And what are now some environmental challenges associated with traditional polymers? So we have on the one side fossil fuel dependency. So the conventional commodity plastics like polyethylene, polypropylene are derived from gas or petrol. This is not per se a bad thing. We have to keep in mind in our global petroleum and gas production, 90% or around 90% is still burned, used for heating or in cars, and only 10% are used to make products such as polymers and plastics. So actually we should lower the burning part and use more this feedstock to make great products, and then we can still burn the plastic part to recover the energy of it. Then persistence in the environment. So it's also a global aim to have worldwide functional plastic waste management system and prevent the littering. So the plastic itself ends up in the nature not alone. It's by itself. It's caused by littering, and this we need to prevent. There are also some toxicity concerns, so potential leaching of harmful substances. Some of you may know bisphenol A with polycarbonate, for example, which is already not in use anymore, or with polyvinyl chloride, the phthalates. More recently, the forever chemicals with PA and polyfluoroalkyl substances. These are all things which needs to be under control. However, now we can generate eco profiles to determine the environmental impacts of all these products, so it gets more transparent and really fact-based. This is a crucial step here. Sustainable polymer solutions. So we have also big potentials when we look into circular feedstock to use the paper waste and generate their new feedstock and generate their monomers out of it. We have bio-based polymers and biodegradable polymers. So there is also what you can see here on the right side, the material coordinate system of bioplastics, where we have lots of potential to move towards the upper bio-based, non-degradable or biodegradable options. We have we can recycle polymers. Also, we have now new commercialized polymers. Just mentioned polyketones as aliphatic polyketones as example, and novel polymer designs and part design. Now we come to the number 4, scientific concepts and methods in life cycle engineering. And here I will present to you 3 concepts. Number 1 is life cycle assessment, LCA, we briefly already mentioned. Then there is material flow analysis, MFA. And the number 3 is eco-design principles for polymers. Let's start with life cycle assessment. So it's a key methodology in life cycle engineering to quantify the environmental impact associated with a product's life cycle. And it has 4 stages. And this is also defined in a standard, the ISO 14040 and 14044. So we have number 1, goal and scope definition. So defining the purpose and boundaries of the study. Second is the life cycle inventory, LCI. So here I collect all the inputs, so resources, energy, and outputs, emissions, waste across the life cycle of my product. Then comes the life cycle impact assessment, LCIA. Here I evaluate the potential environment impact based on different inventory data. And here, some of you may have already heard of this. There is a famous one, is the global warming potential, GWP. There's also resource depletion, water scarcity, and many other categories. And then the 4th step, critical, is interpretation. So I need to analyze the results and draw then the conclusion and use the outcome for my decision making. For example, I can make a contribution analysis, and when I have a system, a product which has 5 different parts, and 2 are made out of metals and 3 are made out of plastics, and then I can make a contribution and see how much the metal contributes to GWP, how much the plastics, and maybe one conclusion is, okay, the metal is higher in GWP, and I can replace it, for example, also with a plastics to lower the GWP and such things. So it's really important then to work with the outcomes. And here I have a application of life cycle analysis outcomes of polymers. So it's 1 kilogram of different polymer resin, and here it's 1 value picked out, the global warming potential, GWP, versus the density of the materials. And when, for example, my part is now made out of a polyamide 6 or 6,6 with a GWP of 6, and I want to have similar mechanical and similar density, I can go down, for example, to a polyketone material type, for example. So it's really important to compare, use the outcomes for comparison and informed decision making. Also, the LCAs are part of environmental product declarations, EPDs, where you also then can read the details. So here on the right side is example from plexiglass solid sheets, and in the EDP is then an life cycle assessment based on the ISO standard 14044. Okay, then we discussed the material flow analysis method, MFA. So it's a simple method to track the flow of materials through a system, and it has 3 steps. So I need to define my system boundaries, then I need to quantify the material flow, and then I need to analyze the material flows. And for example, number 1, defining the boundaries. For example, I can take a geographical boundary, a region like Germany, and then a specific polymers, PVC, started in this geographical boundary. And then I need to quantify the materials flows. I need to collect my inputs, so track the amount of raw materials, for example, in our case, PVC, the production of it into products, the use phases, and also the waste generation. And then and the outputs. So here I need to spend time to collect all the data. And then comes the last step, analyzing the material flows. So I can make different assessments, for example, waste generation assessment. I can identify the sources of high waste generation and potential areas where I can reduce the waste and introduce more recycling, for example. Okay, and number 3, eco-design principle for polymers. So we can say that over 80% of a product's environmental impact is determined in the design stage. It's a crucial state. The one or the other already heard of the 4 core principles to follow. So rethink, reuse, reduce, recycle. And however, there are some design principles for polymers. Number 1 is design for sustainability, also called D4S. So here we focus on minimizing the environmental impact through the whole product's life cycle. Then design for durability. So I can also create a product that lasts longer and reducing the need for frequent replacements. Then design for recyclability. So I can, when I have a system of different materials, instead of 5 different polymers, I can aim to just use 1 or 2 different ones. And instead of gluing or welding together the parts, I can screw it so it's easily for deassemble. And when I have just 2 different polymers, it's easier then to separate and recycle them. Lightweighting, using less material to achieve the same functionality, crucial principle, and also using renewable resources. So I can try also to prioritize bio-based polymers derived from sustainable sources. Okay, now just a brief look into approaches for sustainable polymer management. So I have here selected 3 approaches. Polymer recycling. We can distinguish between mechanical recycling, chemical recycling, dissolution recycling, and organic recycling. Then we can have bio-based and biodegradable polymers. For example, using PLA, polylactic acid, and bio-based polyethylene. However, there are some environmental benefits and challenges associated. So it's, for example, land use for biomass production. And then circular economy for polymers. Here the aim is keep the resources as long as possible in the circle, extract the maximum value. We discussed it in the beginning. Use the petroleum feedstock, gas feedstocks, make great plastic parts out of it, use them as long as possible, and if they're not usable anymore, recycle them or get the energy back by burning them, for example. And design for circularity. So we need to improve the recycling infrastructure and also the waste management structures on a global level. Okay, this brings me to the conclusion of today's presentation and the outlook. So we discussed today life cycle engineering as a key in understanding the full environmental impact of plastic products, really fact-based. Here we can use the life cycle assessment and to really quantify different things. For example, we can really then quantify when I have a PET bottle compared to a glass bottle or other, and really use fact-based decision making. We can use all the other systems like MFA, material flow analysis, and also focus on eco-design principles. We also briefly touched on sustainable polymer management, so discussing recycling option, discussing using more biopolymers, and also building up the circular economy. Okay, so to conclude, polymers are essential part of the solution for a sustainable future and not the problem. Okay, I would like to thank you for being part today of this video, of this exciting topic, designing a sustainable future with polymers, a life cycle perspective. I hope you enjoyed the video. Please like it and subscribe to my channel here, and see you in the next video.